Hello, my name is Lilian. My mentor was Kristen Serrao. My presentation is on random forest regressors for forest fire prediction. So, a quick introduction, like I said, my name is Lilian Pamula, and I'm from Fremont, California, which is in the Bay Area. And I chose forest fires because it has heavily impacted the area in which I live in. So my presentation will be about the interpretability of random forests and how they can provide more insight into predicting forest fires than other methods. So a quick outline of my presentation. First, we'll go over the basics of forest fires and machine learning, and then dive into the methods of my experiment and the results. So quick overview of forest fires. The causes of forest fires. So 85% of forest fires are caused by humans in accidents such as, for example, a loose cigarette or deliberately. Um, all forest fires require fuel, heat, and oxygen to start, and the fuel amounts, the weather, and the topography of the area is what determines the spread of a forest fire. So suppression methods. Natural forest fires are sometimes left to burn because they can be helpful to the ecosystem. However, threats to populations and developed areas are put out as soon as possible. To put out a fire, either the fuel, oxygen, or heat must be removed. And the two most common methods are removing the fuel and heat of a fire. However, suppression is becoming harder because there's been a buildup of uh, forests and vegetation in commonly burned areas, which allows fire to spread faster, as well as the fact that many homes are built in high-risk areas. So the two current methods of prevention and prediction are fuel management, which has a couple of different methods. All three of these methods focus on removing the source of fuel so that fires can't spread as quickly. This includes prescribed burning, which is burning areas before they can be burned by the forest fire in controlled manners. Mechanical thinning, which is using machinery to clear out forests. And mastication, which is turning trees into wood chips that can be spread around the forest, which reduces the spread of forest fires since they don't burn as quickly. The fire weather index is the main way to predict fires. This uses a few different codes and indexes, such as the moisture codes, which determine the amount of moisture in the area, the initial spread index, which provides an initial estimate of how far the fire will spread, and the drought code index, which determines the amount of drying in the soil. I'll explain more about this in the next slide. So here we have a couple of different codes. In my project, we focus mostly on the fine fuel moisture code, the Duff moisture code, the drought code, and the initial spread index. So as you can see, all of these codes take in values from the weather as well as previous observations in order to make estimates about the moisture content of different vegetation in the area, the amount of drying in the area, and then finally an estimate of the initial spread. All of this contributes to the fire weather index. Next, let's dive into machine learning, particularly in conjunction with forest fire prediction. So what is machine learning? It's a subset of artificial intelligence which uses data and algorithms to draw inferences, and then it is supposed to think like humans and learn from experience. So next, let's talk about a loss function, which is a metric for evaluation of how far a prediction is from the actual value. Basically, it's a measure of the error of a function. So there are different types of machine learning, such as supervised versus unsupervised learning. Supervised learning uses labeled training data, and it's what we'll be focusing on in this project, whereas unsupervised training data does not use labels, so it makes inferences from data. Next is regression versus classification. Basically, regression gives a numerical output, whereas classification puts an input into various different categories for an output. We'll be focusing on regression since we're trying to predict the amount of land burned. And finally, interpretability. This is very important since it determines how much we can know about how the machine is making its decisions. For example, basically how much we can learn about the thinking process. So next, let's take a look at random forests and decision trees. So decision tree is basically like a flow chart. It asks yes or no questions to provide a correct output for the given input, and it uses the branching method. Random forests use multiple decision trees and basically take the average of all of their outputs, which makes them more accurate. The important part about both of these methods is that they're interpretable, which means we can see what they're doing. We can actually generate images of the flow charts and look at the decisions they make, which we'll be doing later in the presentation. So now let's look at past work with predicting the amount of land burned by forest fires. So the two most common approaches were using a support vector machine approach and a geometric semantic genetic programming approach. And we can see in these charts that the amount of error. So we want to reduce the amount of error made by the programs, and we can see that geometric semantic genetic programming actually had the least error, followed by support vector machines, and then finally random forests. So random forests were the third least error. However, the first two approaches, which had even less error, were not interpretable, which means we can't draw as many insights from them. Now let's look at some methods and how we created the random forest model. So we looked at fires in the Montecinho Natural Park, which is in northern Portugal. There were 517 data points measuring 13 variables. We can see them here. This included the geographic position, the time, weather, and the fire weather index values, which I talked about earlier, and as well as the final land burned by the forest fire. So the next part is to clean, encode, and sort the data. That means that we have to make sure it has no errors, encode it into numbers which the machine can read, and then sort it into inputs and outputs. Finally, we're ready to create the model. So now let's create and tune the model. First, we can create a default random forest with a default set of hyperparameters. Then we have to try various iterations of hyperparameters. The difference between hyperparameters and normal parameters are that the normal parameters are controlled by the program. It has to learn what the best set of parameters are, and that's how we train the model. However, hyperparameters are parameters set by me, the trainer or supervisor. This includes things like the number of trees in the forest, how many decisions it makes, the number of different inputs that have to be considered in a decision, etc. And we used R-squared error to find the best model, which means it punishes outliers that are very far away from the prediction, whereas outliers that are very close to the prediction are rewarded. Finally, the model is complete. Now let's look at the results, including the importance and implications. So using random forests, we can generate a feature importance list, which basically tells us how important each feature is to finding the final result. So we can see from the importance list, which gives percentages, that the temperature, the Duff moisture code, the relative humidity, and the drought codes are the four most important factors in determining the spread of a fire. The most unimportant factors were the geographic location of the fire in the park, as well as the amount of rain produced. This might seem a little counterintuitive, but it's important to remember that most fires happened during the summer months, which were very dry, and therefore there was not a lot of rain. So now let's look at a few decision trees to see what insights we can draw from them. So the decision trees showed the best decisions that the program decided were the most important to finding the spread of a fire. So here we can see that the first decision was whether or not the temperature was above or below 25 degrees Celsius. And we can see in numerous decision trees that 25 to 26 degrees Celsius was a very common turning point. In the next decision tree, we can see a few different things, such as the relative humidity, which was another important variable, should be between 27 to 8%, which was another important turning point in whether a fire was small or large. Similarly, the Duff moisture code We'll see more examples, but here it's around 140, but the most common variable was around 220. So a lower depth moisture code means that the area is more dry and therefore the fire will probably be bigger. Yeah, so here we can see that the depth moisture code is around 220. And here we can see another example of how the temperature is around 25 to 26 degrees. So now let's look at the implications of this project. So the first thing is that the temperature was the most important factor in deciding how large the fire was, which shows us the importance of managing climate change, which is one thing that determines the temperature of the areas impacted by forest fires. So by reducing the temperatures, by reducing climate change, we can stop the spread of forest fires. Next, it shows its use in various locations. As we could see from the future importance list, the geographic location of the fires was not a very important part. But in future research, we can look at different data from different areas of the world to see if this holds true for all areas of the world. Next, it shows that perhaps the initial spread index is not the best indicator of the spread of a forest fire, since it was relatively low on the list of feature importance. And finally, we can use this to determine the thresholds for large fires by looking at the decision trees to see which values most commonly determined how large a fire can be. We can determine thresholds for whether a larger fire will occur compared to a smaller fire, which alerts natural park services on when a larger fire is more likely to occur. That's it. Thank you for listening to my presentation.